And next up is Ian, who's going to present tail risk in production networks.
Okay, so I want to thank the organizers very much for putting this paper on the program. So the high-level goal in this paper is to think about tail risk and the determinants of tail risk in the economy. So what causes large crashes, where do they come from, what determines their probability, and why do we see equally large booms, right? So we see kind of big movements to the left, say in like the stock market, I'll show you this in a moment, but also in other real outcomes, so like GDP and employment, and we don't see booms that are of the same magnitude. A lot of the goal of monetary and fiscal policy is to avoid those crashes. Equity index options imply investors are highly averse to that left tail. And so what I want to do in this paper is think about what do network models tell us about these kinds of questions. So just to see that asymmetry, this is a plot of returns on the aggregate stock market. I converted them into z-scores. You can see the asymmetry here. You get a lot of movements down to say like -4 standard deviations and many fewer that are that positive. The skewness for this series is about -0.6. That graph died. What I'm going to do in this paper is study large deviations in a general nonlinear production network. So I'm going to take a really, really general network that's kind of like canonical. It can fit a whole bunch of different things, and I think this is a more general. The points here are going to be more general and probably arise in financial networks. But I'm going to study a particular production model. So I'm thinking about large deviations, nonlinear networks. So what does that mean? Number one, when we talk about large deviations, what I mean is we're focusing explicitly on the tail of the distribution of GDP. So this is very much about extreme movements as opposed to small movements. So I'm not thinking about small shocks. This is not a Taylor series. This is going to be something different. Thinking about large shocks and with an approximation that's accurate for large shocks. Number two, we have a network. So this is thinking about rich interactions among sectors and allowing then for a nonlinear response to shocks, that the local and the tail effects are not the same. In terms of contributions, what I'm going to talk about is one, how does the structure of the economy determine crash risk? So what makes an economy more versus less delicate? Number two, what types of shocks cause crashes? What sectors are going to be most dangerous in terms of thinking about crashes? And then three, we can think about what happens in them, but I won't really talk about that today. So what does this model look like? The economy has n sectors. I have this production function where sectorized output, yi, depends on sectorized TFP, zi, its employment, li, and then a CES aggregator over inputs that it gets from other sectors. So xij is sector i's use of good j. It has a weight aij. That's going to determine the structure of the production network, right? It says how much I'm going to want from different upstream sectors. And there's an elasticity of substitution, sigma I. So in terms of what's looking at this, what is going to be most important for driving things? So the network's going to matter through the aij's. The elasticity is going to be central. That sigma is going to be central. When sigma is small, that means that you need all the inputs at the same time. That's where you're getting towards Leontief. When sigma is large, when it goes off to infinity, that's when you're going to a linear production function where you can produce with anything. I'm going to give the consumer Cobb-Douglas utility that's not going to have any real effects here, but they're just going to have weights beta I. I'll talk about these lowercase zi's a lot. That's just the log productivity, where my zi equals 0 is my steady state. I'm going to look at a standard competitive equilibrium. You can solve that either as a planning problem or with prices. And so we'll do it with prices, and to see how this actually works, like how the model works, we're going to be focused on log GDP, so lowercase GDP, and that's just going to be the sum across all the sectors of the sector's weight in final consumption. That's the beta I, right, just from their utility function. The sector's weight in final consumption times the price of that good. Then what's going on here is nominal GDP is just normalized to 1. High prices are going to come from low productivity, and that'll give you low GDP. So we're just going to get a mapping from productivity into GDP. And this formula here for this PI, that actually determines just the entire solution to the model, right? If you can solve that recursion, you can solve the whole thing. And that just says that the price of good I, so sector I is good, depends on sectorized productivity. So if sectorized productivity goes up, Zi rises. Sectorized price falls, that's good for GDP. But then the price of sectorized good also depends on the prices of everything that it uses as an input. Right? So it's going to be the sum across all of those inputs of the log prices, those PJs, That elasticity of substitution shows up again, the sigma I, and the weights, the aij's, show up. And so we just get this little recursion. And like fundamentally, when you solve the model, you're solving that equation, and you're trying to talk about what that equation is. And that's going to map into GDP. And so you can see sort of immediately just from that equation, again, increases in productivity ZI will have direct effects on GDP, and they'll also have indirect effects, because if the price of good I falls, that's good for all of the downstream sectors. So for small shocks, when the ZIs are close to 0, we get this simple linear recursion. So this is what you normally do in production networks. You either linearize or you set the elasticity of substitution to 1. And in that case, then, what determines the price of good I is, again, its productivity and just the sum of all the log prices upstream, and you can just solve that, right? That's just a linear problem. It's just a matrix inversion. The result from that is that shocks propagate downstream, weighted by those aij's. So I want to do something, well, so you do that, and so this would be the normal way you'd approximate a model, right? Is we have productivity in some sector, some combination of sectors on the x-axis. The blue line in the middle is the true model. I could do a linear approximation, that's the red. I could do a second order approximation if I want, that would be the black dotted line. But as your shocks get big, any Taylor series is going to get worse. And in fact, the Taylor series isn't even convergent here, so adding more terms doesn't help. The model's not analytic. So what happens if I have big shocks? So I want to come at this from a totally different angle. What I want to do is think about, take my vector of productivities, my z. So I'm just stacking the log productivity in every sector. That always has a polar representation, where I can write z as theta times some t, where theta is just going to be a direction in productivity space, right? So it could be I hit every sector at the same time, I hit one sector, I hit half the sectors. Whatever combination you want, that's going to be a theta. So theta is in Rn, it lives on the hypersphere. T is going to be my magnitude, so t is just a scalar, it's actually going to be positive. It's not a real number, it's only on the positive axis. So theta controls direction, t controls magnitude. Productivity in sector I, Zi is theta I times t. And then I'm going to guess that these prices all converge to a linear function of t. So my pi's converge to phi t, phi I times t. What are you doing there? So what we're going to get is, remember before, for my local approximation, I have this little recursion that my price depends on productivity and the price is upstream. You still get that here. So in the more general setting, what I get is that the prices, laser point. Does this work? See, I don't like this one bit. I don't know, are they here? Did Yale invent this thing? Because they got really offended when I said I didn't like this pointer thing, because you can't see the rest of the slide. I'm like, I can't see the rest of the slide, but I can't, so. Anyway, I'll stop. So there's my price. The price still has this, is still recursive, right? The price still depends on my productivity. When the productivities go up, right? So if theta goes up, my price falls, and I still care about what happens upstream of me, but instead of caring about everybody with that sum, what it turns out is that if that elasticity of substitution is not equal to 1, I only care about a single sector upstream of me. If the elasticity of substitution is greater than 1, so if I'm more substitutable than Cobb-Douglas, then all that matters is my best input upstream. What is the cheapest thing? If that elasticity of substitution is less than 1, so I'm in the direction of Leontief, then I effectively just am Leontief. All that matters for driving my price is what is the weakest of my inputs upstream. What this is saying is that when the shocks get big, this entire thing looks like either Leontief or linear. That all I care about is the most extreme of my inputs, and nothing else ends up mattering. And so what's nice about this then, or a couple of things that are nice about this, is that there's a lot less information than I need. I don't actually need to know the values of the A's. Those production weights don't enter into this, except for in the knife edge case when I'm exactly Cobb-Douglas. The production weights determine which inputs I use. That's going to matter. But the exact weight on the input has no effect on anything. The exact value of the sigmas doesn't matter. All I need to know is whether they're above or below 1. After that, I don't need to sit here and estimate the precise value of every single elasticity. I do need to know my intermediate expenditure share because I am Cobb-Douglas here between labor and materials, but the exact values of these other things don't matter. So formally what you end up actually getting is that we can write, what we get is that asymptotically, it's this equation, GDP is a linear function of the magnitude of the shocks t, where that linear function is going to depend on the direction that I'm looking at. So what's happening is that asymptotically, as the shocks get big, GDP converges to some line, right? Even though you have this big nonlinear thing where there's all sorts of stuff happening, all of it kind of washes out in the end and you converge to something with this lambda of theta, and the convergence ends up, you go to 0, sort of similar to what a Taylor series does, but instead of for the shocks going to 0, we're thinking about the shocks going to infinity. That's what that t to infinity is doing. And so this then is what the approximation is doing. This is how I'm thinking about GDP, is instead of that local Taylor series, I'm fitting with that dotted line that's going to be exact as I go out into the tail, and it's actually going to be worse for the small shocks, right? Because this is crazy for small shocks. For small shocks, or for like what this is saying is that for whatever the combination of shocks is, I'm only thinking about one upstream sector. The point is that that's going to work when things go crazy. For local things, you're just thinking about like some random Tuesday, really bad idea. There are two comparative statics that you can get out of this that I'll talk about going forward. One is that this lambda, so that's the sensitivity of GDP to a shock. GDP gets more sensitive when any elasticity transitions from less than 1 to greater than 1. That basically GDP is going to be greater when there's more substitutability. You're going to have more output when substitutability is higher. Number two, when the set of inputs used by a sector grows, GDP is going to be higher if the elasticity is greater than 1, and it's going to be lower if the elasticity is less than 1, right? This is just saying if I have more complements, I have more fragility. So you can think about semiconductors, for example. All of a sudden, they didn't used to exist. They now exist. They're obviously good for output on average, but now all these different sectors are sensitive to the same input, right? We're finding out that like if you want to close the tailgate of your car, turns out you need semiconductors, right? They show up just like everywhere. And that ends up increasing the fragility of this system. How much time do I have?
8.
I said I had 10 like 10 minutes ago. I'll take 8. Not that in a good way.
You don't have to.
No, I want it. I have probably too many slides.
No, it's 7.
Okay. So I'm going to take that thing. So I'm just trying to think about if I'll stop muttering. So I want to think about tail risk. I want to think about the probability of one of these big events, right? Of a crash. How likely are crashes and what determines how likely crashes are. So to measure tail risk, I'm going to need a distribution for the shocks. And basically what we're going to do is say that in some direction, theta, there's a cumulative distribution function, f. And there's also going to be a distribution over the directions for the shocks that you get, right? So this just gives you a very, very general way of thinking in like a multivariate setting about extreme events for the fundamental shocks. You could obviously totally restrict this to just multivariate normal or something like that if you want. This is one particular special case of a much more general result that shows up in the paper. So suppose that the tails of the shocks have this exponential type form. So they're exponential with this exponent kappa on the t inside the exponential. So the normal is going to look like that, the exponential is going to look like that, y more generally looks like this. Then what you get is the probability that GDP falls below some number x as that x goes off to infinity. So I think about what is the shape of the tail of the distribution of GDP as I get further and further out. It turns out that that probability depends not on the entire economy, not on everything that's happening, but actually only on essentially what is the single worst possible combination of shocks. That I'm looking at this max over theta, so over all possible directions of the impact of the shock on GDP. So what is that actually saying in words? What it's saying is that for this big, big class of distributions, first of all crashes turn out to look the same. Second of all, if I want to know what determines the likelihood of a crash, what I care about is something like this stress test sort of idea, that there's one direction that is going to be most harmful to the economy, and this tells you how to find it, which is it's the direction that has the largest asymptotic effect on GDP. So the last thing I want to do is think about what those asymptotic effects are. So if I was going to measure the centrality of a sector, right? There's one thing that we like often do, which is that we look at sales shares, right? So in like the standard first order result in a network model is that the first order effect of a TFP shock to a given sector is just its sales share, right? Its share of its sales divided by nominal GDP. What I want to think about here is not the local effect when the shock is big. I want to think about the effect, or not the local effect when the shock is small. I want to think about making the shock really big. So I want to think about the limit as productivity goes off to minus infinity of the change in GDP. So I want to think about this like asymptotic sort of derivative, and I'm just going to define that to be my gamma L. So that's what I'm going to call the tail centrality for sector I. And the result then is that you can actually calculate that directly from this tail approximation that I showed you from that lambda. It's the asymptotic effect of a shock to a given sector. One nice result that we have is if all the elasticities are less than 1, so if everything is complementary here, then what is going to determine the tail centrality of a given sector is what fraction of GDP is downstream of it and how far. Sectors that have more of GDP downstream, so think about something like electricity that's used as an input for everything. Electricity is going to have a very large tail centrality. Something like restaurants where nothing is downstream of restaurants, they have essentially no tail centrality because nothing else relies on it. You shut down the restaurants, you don't shut down anything else. If you shut off electricity, everything's over. And so what this is doing then is trying to measure that tail centrality based on that formula. So this is assuming that the elasticities are all less than 1. On the x-axis, what I have is the sales share this is the 2012 input-output tables. I have the sales share on the x-axis, and then I have an estimate of the tail centrality on the y-axis. And I picked out the top 5 sectors and kind of in both dimensions, and I'm labeling those. So petroleum refineries are important in both dimensions. They have a very large sales share, and there's a lot of stuff downstream of it. Hospitals have the second largest sales share, but they have absolutely nothing downstream of them. Nobody in the input-output tables uses them as an input. It's not to say hospitals aren't important, but they're important through the utility function and not through the production network. Scientific R&D is the same. We don't have capital here, and so any kind of R&D type stuff is going to have kind of a low propagation. The same goes for restaurants. I think restaurants are the next ones after R&D. On the other side, you get these things that have really high tail centrality relative to their sales share. So electricity is one of them. We don't spend a ton of money on electricity, but everybody uses it. And then you get these 3 professional services, which I think of, to me, they're like a kind of like a gut check for how do you feel about this model, and also how do you feel about the estimation. So we get legal services, accounting and advertising and PR, and accounting. So the legal services, what this is saying is that every sector in the input-output tables is spending money on legal services, right? Everybody buys legal services. I would not have thought that this would show up at the top, but to me, I'm actually totally comfortable with this, and I sort of like it in the sense that what it's doing is it's illustrating that we all use this thing, and you can kind of imagine that if we shut down the legal system more broadly, we have a problem, right? We need contracts, we need enforcement of property rights. Same with accounting. If all of a sudden we didn't have accounting, that feels like a thing that we need in order to do business, right? This is one of those major innovations in the history of business. Advertising and PR, that doesn't feel right? We could shut down advertising. Probably we don't shut down the economy. The explanation for that is that elasticity of substitution is not less than 1 there, right? That is not actually an input that I need to mix with everything else in order to be able to produce. This graph, we're assuming all the sigmas are less than 1. It's obviously an extreme assumption, and I think it's really unreasonable in that particular case. So the point of this then is to understand tail risk in a general nonlinear production network. I get this approximation that lets me think about the effects of shocks when they get really big. This gives us then a method for measuring tail risk in overall GDP and also thinking about the influence of individual sectors. What you get out of it is that where crashes come from is really complementarity. In the absence of complementarity in inputs, sector-level shocks are not going to create left-tail events in GDP. You need this complementarity, and you really need shocks to universal inputs to end up doing that. Okay, thanks.
Great, thanks, Ian. This question is Alex Uinski.
right, thank you, Ian, for arranging the presentation and for opportunity for me to read this paper. So what I'm going to do is maybe something maybe unusual, maybe orthogonal or whatever. I was trying to figure out how this whole literature works, and that's sort of the fruit of my thinking about a variety of different things. But hopefully I'll be able to put a little bit more in a broader context and also think about how to develop this literature in a variety of dimensions. Some special thanks to Georgi Ryabov, who is my co-author on this. He's in Kiev at the Institute of Mathematics, and to Sasha Zeman, who is another co-author on different stuff, who is a student at MIT in mathematics. All right, now let's start with the following idea. So how many of you like oranges? Okay. So imagine you have an orange. And imagine that you peel the orange, right? So this orange stuff on the top is the peel. So if you hold an orange, if you peel it, how much of the orange will you have left? John?
80%.
Like most of it, right? And you have a very thick. So most of the orange is going to be left. What about n dimensions? So what happens if you peel an orange that exists in n dimensions? N-dimensional orange. How much of the orange is going to be left? Much less. Much less. Okay, so what's this? Okay, so Leonid knows. All right, so in fact, if you peel an orange in n dimensions, actually almost nothing is going to be left. So this is a nice picture from Thomas Stromer from UC Davis. So how do we see this, and what does it have to do with the networks? All right, so let me first show you why when you peel the orange, almost nothing is left. So suppose we have n random variables, epsilon1 to epsilon n. Suppose they're independent. Sorry, just do one back. Oh, I guess this is an older version of the paper. An older version of the slides didn't get updated. Whatever. So, this is a fact about n-dimensional oranges, and what it has to do is the following. So, what this literature on networks really tries to do, or at least a part of the literature on the networks that is interested in whether the micro-level shocks have macro effects, is the following. Suppose we have n random variables, epsilon1 to epsilon n, and we have a function. And this function is an n-dimensional function, so it maps Rn to R, to a number. And in particular, we're interested in the properties of the random variable. So y is like a GDP, and f and epsilon is like the shocks to each individual sectors. The question is, under what conditions on the random variables and under what conditions on f we will have the GDP y to deviate significantly from its mean, from the expected value of this function. So this is the essence, in fact, of why microshocks have macro effects. So Ian talked about one particular example of why these things may matter. He talked about large shocks having large effects. What I'm going to try to do is I'm going to try to think about whether one could unify and think about this literature from one set of interesting mathematical tools of whether the microshocks are going to have macro effects. And the discussion is going to be structured the following. So I'm going to go back and try to think about this problem somewhat abstractly, and in particular I'm going to introduce the set of the tools called concentration of measure or concentration inequality that allows us to think about this kind of questions. I'm going to start with actual linear functions and with the law of large numbers, and I'm going to ask what happens if the number of sectors n, or the number of these random variables, goes to infinity. I'm going to see what's the scope of the law of large numbers is. It has nothing to do with concentration of measures yet. And then I'm going to ask the following question. How far is something from its mean if the function is nonlinear, in particular, and if we are not in the situation where we have infinitely many of the random variables, but we have a finite number of n. And the powerful set of tools called concentration inequalities allow us to answer this kind of question. So, in particular, what I'm trying to say is that the things like what happened in Ian's work can be thought of as the following context. Under what conditions this concentration inequalities do not hold are going to be exactly the conditions under which micro effects are going to have macro consequences. All right, so now let's start with just warming ourselves up with the law of large numbers and seeing how far we can push the law of large numbers. So let's first start with just simple average, independent, identically distributed random variables which have finite variance. So we have n random variables, they're identical, so they have the same variance, let's call it sigma squared. So the law of large numbers says the following. So the average, or the linear function of this variable, so epsilon 1 to epsilon n, divided by n, converges to its mean as n goes to infinity. Okay, the classic law of large numbers, which you remember from introductory statistics and from econometrics classes. One thing I want to emphasize here, I'm going to do this mystery thing, is that influence of each epsilon I is going to be 1 over n. Okay, so that's something to keep in mind, that's important. So now let's push a little bit further, so for fine. So suppose we don't have just the identical sum with a weight 1 over n. Suppose we have some weights w, and this weights w can depend on, say, how many of these variables are. So it's going to be w of n, this weight sum to 1. Here, the influence of each observation, which is the just derivative of this linear function, is just its weight. Okay, so the influence of each individual function is important. So then the law of large numbers basically says the following, that this weighted average converges to its mean in probability as n goes to infinity if the total influence, so the sum of this weight squared, goes to 0. Okay, so we can push a little bit further. We don't have to look at just normal average. We can look at just the weighted averages. Law of large number holds. Suppose we have not identical variables. Okay, so not identical variables, we still have the law of large number holding in a slightly different form. So suppose that each individual variance is sigma I squared, each individual mean is mu I, which is just the expectation of epsilon I. The law of large number again holds for n going to infinity. And what you'll have is you'll have this average, epsilon 1 to epsilon n divided by n, converging to 1 over n, the sum of the means. If you have properly declining sum of the variance. So in particular, the sum of the variances should be a little of n squared. Okay, so we can push the law of large numbers with non-identical stuff. So if you want to think again back to the micro shocks, even if the shocks are not identical, under proper condition of its variances, you will still have no macro influence. What if you have fat tails? So with the fat tails, it's problematic. So with the fat tails, the law of large numbers doesn't hold. Suppose we have a Cauchy distribution. This is the PDF. Then epsilon 1 plus epsilon n divided by n is also going to be a Cauchy. Okay, so it means it's not constant. So it's a random variable, it doesn't converge. So infinite variance of fat tails is one example where micro shocks are going to have macro consequences, at least for the simple averages. Suppose we have not independent shocks. Okay, if we have not independent shocks, suppose all, for example, epsilons are identical, then their average is going to be just epsilon. So there is no hope for this thing to converge to a constant. All right. Still, even without independence, we can still have the law of large number holding. So for example, we have weak dependence. So we have the variance of the sum going to 0. Then the law of large numbers for n going to infinity is still going to hold. So what does it mean? So let's just compute the variance very simply. It's going to be the sum of the variances plus the sum of the covariances. If the covariances somehow are 0 for most of the pairs, you still will have the law of large numbers holding. For example, if the influence, the function f here, if the influence of I on j declines if say the sectors I and j are far away, then we still will have the law of large numbers. Okay, so that's what I'm using. We have talked about what happens for n going to infinity. We have seen the scope of the law of large numbers. We already have a feel of when the microshocks can have macro consequences. Now, what I want to ask is a slightly different question. So, suppose that the law of large numbers holds in some sense. So we have the mean, so the average is equal approximately, or equal in distribution if you want, is equal to the expectation. How far off it's going to be? I mean, if n is equal to infinity, we know it's exactly that. But now suppose we have not infinitely many sectors, but a finite number of sectors. For example, we have n. How far are we going to be from the average? The first instinct to do will be just to use the central limit theorem. Central limit theorem tells you, well, we converge to the Gaussian distribution, but that theorem only works for n going to infinity. Moreover, one can show that the error of approximation, how close you are to the Gaussian, is actually very poorly behaved. So for any limited n, you can be really far away from the normal distribution, from the Gaussians. It's called the Berry-Essen central limit theorem that gives you the precise answers for this. So what can we say for the realistic question when n is finite, when the number of sectors is finite? Can we still have some idea of how far away we are from the mean? And for this, the sequence of results I'm going to show you next, which are called concentration inequalities, is useful to use. So the simplest one is the Chebyshev inequality. So what does it do? What does it do is the following. So it says, let's find the probability of the average to be different from its mean. And there is some level C, so it's like the deviation is larger, to be larger than the level C. So the Chebyshev theorem says the following, or Chebyshev inequality says that this thing, so if the second moments exist, the variances exist, then this probability of the large deviation declines as C squared. Okay, and this is valid for any n, but you need to have the second moments to exist. The decay is not great, but the probability of a large deviation at least is quadratically declining in the size of this deviation. Let's do something a little bit more sophisticated. Suppose that the higher moments exist, then you can actually bound the probability of the high deviation, the probability of the macro consequence, by c to the power n, if higher order moments exist. If exponential moments exist, then it's a little bit more complicated result, but basically, in many cases, it says that the probability is exponentially declining. So you're very close to the Gauss. Okay, now let's ask a slightly more general question, which is actually kind of cool. So it's a Hovden bound, and Alireza, did I see Alireza somewhere? He's gone. So Alireza used this actually in his paper, that's a Moglo, or a version of this, for n going to infinity, or a version of this called Chernow bounds on this. But if you have the bounded variables, bounded individual shocks, then you have the so-called Hovden bound, where you can say that again, for any n, you can bound this probability of the large deviation exponentially. Okay, so you will actually be the probability of this macro deviation being large is declining very, very fast, declining exponentially. And you can do it also without independence. It's called the Azuma-Hovden inequality. All right. So this is very interesting, and what we have done is we have seen how one could think more generally about the microcons of the shocks, even for the finite number of the sectors. Now let me do something more sophisticated. So what would happen if F is nonlinear? That's actually the central part that Ian emphasized in his work. So most of the people think about this input-output models either linear or maybe up to the second approximation. Or something like this. What can we say in general for the nonlinear terms, for the nonlinear transformations happen? So the key idea here is the following. The key idea of concentration inequalities is the following. If I can somehow bound the influence of each individual shock in terms of this function f that puts them together, that maps them into the macro consequences, we will have very nice bounds. So let me give you one example like this called Magdiarmid inequality. So Magdiarmid inequality does the following. Suppose we have a function of n variables, and we're just going to concentrate on just one variable, epsilon I. I'm going to replace it with epsilon I prime. And if this impact is bounded by Ci, I essentially get the exponential bounds. So f is nonlinear. So if I somehow put a bound on the derivative, in a sense, or the bound on the influence of each individual shock, then I have this very powerful inequality saying even for finite n, I can bound the influence of the microshocks on the macro variables. In fact, it implies the Hopton bound. All right, now let me show you how far you can push this. So I'm not going to talk much about this, but I'm going to give you the flavor. So there's a very nice discussion by Terry Taos, very famous mathematician at UCLA, about all of this. And what you have is, if you have a Lipschitz function which has very nicely behaved derivatives, then, and if you have the shocks which are being Gaussian, then that function of the shocks, the Lipschitz function of the shock, essentially looks like a Gaussian themselves. The more sophisticated version of this is called this very famous Talleyrand inequality. It says that even if you have Bernoulli variables, and if you have convex Lipschitz functions, the function of it concentrates like a Gaussian. So basically everything looks like this peel of the orange. So you just concentrate this very narrow band around the mean. So what's the bottom line? So the bottom line is this. Essentially, the big question, an example of what Ian is doing, is how microshocks translate to the macro consequences. And the concentration of measure theory, concentration of measure inequality, tell you that under some very non-onerous assumptions, the impact is always going to be very close to the mean. So the name of the game in asking the question of why microshocks matter for macro is in seeing what assumptions in this concentration inequalities are not satisfied. So the right way to think about the microshocks having macro consequences is in terms of concentration of measures. And it's very powerful, very nicely developed literature that gives you all kinds of super powerful tools for understanding, even for the non-asymptotic, for n being finite, what the bounds are of micro consequences. So micro consequences of macro shocks are like the peel of the orange and is like the concentration inequality. So that's my sort of broad overview of this discussion, and Ian is one example of showing where exactly these things fail. Did I make it on time?
Yeah, you're good. Thank you. All right, Ian, you want to take some questions and or respond?
Yeah, I mean, so like in terms of response, this is all, I mean, the like amount of content in here is sort of incredible. And this, so the amount of content is sort of incredible, and like these are like super useful ideas. And I think, is there any way to keep these? Can whoever's moving? Can I just keep this? I guess it's gone. Doesn't matter.
Slides disappear?
I can still see this stuff.
Okay.
It's because there's somebody like just touch it, like up
Yeah,
above.
touch the screen.
No, it doesn't work like that. There's somebody doing things. Somebody who's not here has been doing all of this. And so when I like criticized the clicker, I thought that nobody was here,
Their
but in
voices.
fact they were.
Okay.
Yes. So because they're moving, they're changing slides now, but they're ignoring them. Because I criticized the clicker. So the concentration of measure stuff is super interesting. Like there's this, I think this, I need to think more about like this question of how do you break, like what exactly here is breaking those things. So like what is, like why, to what extent do those results not hold? Related to those results is the like extreme value type literature, thinking about like tails of distributions. And so the paper very much explicitly focuses on that at the moment in terms of like in thinking about probabilities of extreme events. And so those two literatures are kind of like broadly related. And so but I need to look much more closely at the stuff that Oleg was talking about. But like, you know, I think that's where I'm going to leave it for the moment.
So can you talk about like the similarity and distinction between eigenvalue centrality and tail centrality? And I'll tell my motivation. So, informally, right, eigenvalue centrality means if there's a block in the network, what's the probability it's going to pass through me? So actually, downstream firms are going to have larger eigenvalue centrality. But what if I just transpose the network and then apply eigenvalue centrality? Wouldn't that be very highly correlated with the tail centrality you're suggesting?
So the part of what's going, so that I can draw one connection, and I don't know whether it exactly gets at what you're saying. I want to think hard. Like, I see where you're going, and I need to think harder about it. I'm not comfortable totally addressing it right now, but I can address a neighboring point that might help a little bit, which is that we have like the normal kind of local centrality that we think about in terms of sales shares. This is that, like the thing that I'm calling the tail centrality is exactly that, but for a different network. So part of the like insight when you actually like work through the math here is that like you're in a nonlinear model, and so this like when you think about linear things like that, right? That's like kind of like that's taking the way you're talking about is that like I have this linear structure, right? You're talking about eigenvalues and things like that. In a nonlinear model, that's going to be valid locally, but not elsewhere. So this is saying when I make the shocks big, what happens to the network? And then I could absolutely think about the eigenvalue centrality or any other measure of centrality for this special network that we're getting when we go out into the tail. So on some level, the like fundamental insight of the paper is just to say, and it's like when you think about it, it's kind of obvious, is that when the shocks get really big, the network is different. And it's not the same network, and that like if I care about extreme events, that's the thing I need to worry about, not the local stuff. And so you can totally, so like what you're saying, I think you can totally, like I want to think harder about it, but like in general, you can measure these things in this, in these like, it's basically a restricted network that you get out in the tail.
Couple of related, this really cool paper, a couple of related ideas. So one is, this sounds a little bit to me like the O-ring theory of growth. So this was Chad Jones years ago, made the point that like the whole space shuttle blew up because one ring failed, right? And so that's sort of a theory of tasks and workers as opposed to inputs, like you've described them, but maybe your model could also be about tasks and workers, and might also say something about wages and so like, you know, who are the critical workers, or are they all critical? And then the other thing it made me think of is that, you know, that example then led me to think about if tasks or inputs often fail, wouldn't you get positive skewness? Because it would be a fairly rare event that everything worked according to plan. And maybe that's a theory of like unicorns or something. Like there are a million ways that new businesses go wrong, but gosh, when it all comes together and nobody screws up, you know, that's when you get the, you know, the Facebooks and Googles of the world.
I see what you're saying with the latter. That's going to be a little sensitive to precisely how you meant. So this is not to say that what you're saying is wrong. Like I think what you're saying is right, and it's that the skewness can be a little tricky, right? In terms of whether are we thinking about like really the tail, or are we thinking about like the third moment, and that those things don't need to be exactly the same. And I think you may be pointing to a tension between the two. But so I want to think more about that because like in this world, like you are like in this model where everything's a complement, you are getting that, right? That you need everything to go right, and so the right tail doesn't happen that much, and the left tail kind of happens more. And so the mass is definitely shifted to the left, but it also just turns out that the length of that tail is longer at the same time. Also, the O-rings were huge. They were all the way around the SRBs. They weren't like little ones. It wasn't a little O-ring. It was like a giant O-ring. It was like this thick or something. But like that thing cracked, and they actually knew. They knew. It was like a whole. That was like scandalous. Because they left it out in the cold. Anyway, but anyway, it was a big O-ring. I get excited about space. I'm sorry. Yes. Yeah.
All right, great.